How a SKS works, invented by Sergei Simonov in 1945. In the winter of 1945, inside a Soviet engineering workshop still defined by the cold geometry of a high-stakes era, Sergei Gavrilovich Simonov stood before a workbench covered with metal components and technical drawings. The air carried the scent of machining oil and heated steel. Before him lay a prototype rifle, slender, mechanically elegant, and built around a principle that challenged the assumptions shaping most equipment development at that moment. The device was self-loading, meaning it would chamber the next round automatically after each discharge. Yet it was not fully automatic. It would fire once per trigger pull, not continuously. This restraint was a deliberate choice, not a compromise. The rifle was chambered for a cartridge smaller than the full-power rounds used in traditional bolt-action systems, but larger than pistol ammunition. This intermediate cartridge, 7.62 39 mm, had been developed to address a challenge Soviet planners had observed across years of active service. Personnel rarely needed the range and power of heavy rifle cartridges, and when they engaged in automatic fire, they exhausted supplies and lost precision. The equipment Simonov was refining represented a different path. It would provide infantry the ability to fire rapidly without manual cycling, but it would not encourage the kind of rapid consumption that emptied magazines in seconds. The contradiction was this. The Soviet Union had just witnessed the effectiveness of rapid-fire equipment in close-quarters engagement, yet Simonov was designing a rifle that intentionally rejected full auto capability. His reasoning was grounded not in tactics, but in engineering logic. A self-loading rifle offered speed and efficiency. A semi-automatic mechanism reduced wear, conserved supplies, and allowed users to maintain aimed fire. The fixed 10-round magazine, loaded via stripper clips, reinforced this philosophy. It was not designed for sustained output. It was designed for control. Simonov examined the gas piston assembly, a short-stroke system that would tap pressure from the barrel and convert it into mechanical motion. The bolt carrier was designed to tilt and lock into the receiver, a mechanism simple enough to be produced in state facilities and robust enough to function in extreme conditions. Every part had been calculated to balance reliability, ease of production, and maintainability in the field. The equipment did not ask for more than it needed. It worked within the constraints of Soviet industrial capacity and the realities of infantry engagement at ranges between 100 and 400 meters. Around him the workshop was quiet. No voices, only the soft hum of machines and the occasional metallic click of components being fitted together. This was not a moment of triumph. It was a moment of focused problem-solving. The rifle would need to prove itself not through theory, but through rigorous testing, through cold, mud, dust, and the judgment of officials who were not yet convinced that a semi-automatic rifle could meet the needs of a modern force. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. Sergei Gavrilovich Simonov was no stranger to equipment design when he began work on what would become the SKS. Born in 1894, he had entered the field of mechanical engineering in the early Soviet period, when the nation's industrial base was fragmented and its technology lagged behind other powers. Simonov had worked on various automated projects throughout the 1920s and 1930s, including experimental rapid-fire systems and self-loading rifles. His designs were methodical, grounded in mechanical principles rather than intuition. He understood gas-operated systems, locking mechanisms, and the challenges of manufacturing at scale with limited resources. By 1945, the pressure on Soviet designers had reached a critical point. Recent global events had exposed weaknesses in the standard infantry rifle, the Mosin-Nagant bolt action, a tool that had served since the late 19th century. It was accurate and powerful, but it required manual operation between shots, a limitation that placed personnel at a disadvantage against those equipped with semi-automatic or automatic systems. The Soviet Union had produced high-rate-of-fire tools like the PPSH-41, which provided rapid coverage at close range, but these lacked the distance and precision needed for most engagements. There was a gap in capability, and it needed to be filled: the development of the 7.62 to 39 mm intermediate cartridge created the foundation for a new class of equipment. This cartridge was shorter and lighter than traditional rounds, which meant personnel could carry more supplies, and the recoil was manageable enough to allow for controlled semi-automatic or even automatic fire. Engineers elsewhere had pioneered this concept with the STG-44, and Soviet planners recognized its potential. But the question remained: what kind of device should fire this cartridge? Should it be fully automatic, or should it be semi-automatic, offering speed without the waste of rapid fire? Simonov believed the answer lay in restraint. His design philosophy prioritized reliability, ease of use, and efficiency. A self-loading rifle would give personnel the ability to fire rapidly without the complexity and supply consumption of a fully automatic system. It would be simpler to train on, easier to maintain in the field, and less likely to malfunction under harsh conditions. The fixed magazine, rather than a detachable box, would keep the device lighter and reduce the risk of losing critical components in the field. These decisions reflected the material realities of a nation that had been through intense hardship and needed equipment that could be produced quickly, used by those with minimal training, and maintained with limited resources. Yet Simonov's approach was not universally accepted. Within the defense establishment, there were voices arguing for fully automatic capability. They pointed to the success of rapid-fire tools in urban settings and close-quarters struggle. They questioned whether a semi-automatic rifle could provide sufficient coverage in modern scenarios. Simonov would need to prove that his design was not a step backward, but a calculated step forward, a tool that balanced lessons from the field with the constraints of engineering reality. The operating principle of the SKS was elegant in its directness. When a round was fired, high-pressure gas generated by the burning propellant traveled down the barrel behind the projectile. A small port drilled into the barrel allowed some of this gas to escape into a cylinder mounted above. Inside this cylinder was a piston, a short, solid component designed to move rearward under gas pressure. This was a short-stroke gas piston system, meaning the piston traveled only a brief distance before stopping. Its motion was brief, but sufficient to transfer energy to the bolt carrier. The piston struck the bolt carrier, driving it rearward. As the carrier moved back, it rotated the bolt, unlocking it from the receiver. The bolt and carrier then continued rearward together, extracting the spent case and ejecting it through a port on the right side. A recoil spring, compressed during this motion, then pushed the bolt carrier and bolt forward again. As the bolt moved forward, it stripped a new round from the fixed 10-round magazine located beneath the receiver and chambered it. The bolt rotated back into its locked position, and the device was ready to fire again. The entire cycle took a fraction of a second and required no manual intervention beyond pulling the trigger. This system was not revolutionary. Gas-operated, self-loading rifles had existed before. What made Simonov's design significant was its simplicity and its adaptation to the intermediate cartridge. The short-stroke piston reduced the moving mass inside the device, which improved reliability and reduced wear on components. The tilting bolt-locking mechanism was robust and could tolerate dirt, mud, and extreme temperatures. The equipment could be disassembled in the field without tools, a requirement for any device intended for mass use by personnel who might need to clean or repair it under difficult conditions. When Simonov presented the design to officials, the response was mixed. The self-loading mechanism was appreciated, but questions remained about the lack of automatic capability. One senior officer reviewing the prototype at a testing facility outside Moscow remarked that personnel needed the option to fire continuously in close encounters. Simonov's counterargument was grounded in data. Automatic fire consumed supplies too quickly, reduced precision, and required more training to use effectively. A semi-automatic rifle offered a better balance between speed and control. It allowed the user to fire as quickly as they could pull the trigger, which in practice was nearly as fast as most could accurately manage. The resistance was not easily overcome. Doctrine was evolving, and there was no consensus on what the standard infantry tool should be. Simonov's rifle would need to prove itself through rigorous testing, not just mechanical testing to ensure function, but field testing to demonstrate that it met the practical needs of the personnel. The engineering was sound. The question was whether the philosophy behind it would be accepted. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. Testing began in early 1946 at proving grounds where temperatures dropped below freezing and where mud, dust, and moisture were deliberately introduced to simulate field conditions. The SKS prototype was operated thousands of times, disassembled, reassembled, and subjected to stress tests designed to reveal weaknesses. Engineers monitored the gas piston system for signs of fouling or excessive wear. They measured the force required to unlock the bolt and the consistency of the extraction and ejection cycle. They tested the device after it had been submerged in water, buried in sand, and left exposed to freezing rain. The results were promising but not perfect. Early versions of the piston showed signs of carbon buildup after sustained use, which could impede its movement and cause malfunctions. Simonov revised the gas port dimensions, slightly increasing the diameter to ensure that gas flow remained sufficient, even when deposits accumulated. He also refined the shape of the piston head to allow it to shed carbon more effectively. These were small adjustments, but they had significant effects on reliability. Material selection was another critical consideration. The receiver needed to be strong enough to withstand the forces generated during use, but light enough to keep the rifle manageable for those who might carry it for hours or days. Simonov specified stamped steel for the receiver, a choice that balanced strength, weight, and manufacturability. Stamped components could be produced more quickly than milled parts, which was essential for a nation rebuilding its industrial capacity. The barrel was made from chrome-lined steel, a decision that extended its service life and reduced erosion from repeated use. The fixed magazine presented its own engineering challenges. It needed to hold 10 rounds securely, feed them reliably into the chamber, and remain accessible for cleaning. Simonov designed the magazine to be loaded from the top using stripper clips, metal guides that held rounds in alignment and allowed them to be pushed down into the magazine quickly. This system was slower than changing a detachable magazine, but it eliminated the risk of losing critical components in the field and simplified training. Personnel could reload without looking down at the device, a skill that could be taught in a matter of hours. By late 1946, the SKS had passed most of its technical evaluations. The device functioned reliably across a range of temperatures and environmental conditions. It was accurate at ranges up to 400 meters, which covered the vast majority of infantry engagement distances. The semi-automatic mechanism allowed users to maintain a steady rate of aimed fire without the recoil and muzzle climb associated with automatic systems. The simplicity of the design meant that it could be produced in existing factories without requiring extensive retooling. Yet acceptance was still not guaranteed. In parallel with Simonov's work, another designer, Mikhail Kalashnikov, was developing a rifle that offered selective fire capability. This equipment, which would eventually become the AK-47, could switch between semi-automatic and fully automatic modes. It represented a different philosophy, one that prioritized versatility over specialization. Officials were watching both projects closely, evaluating not just the technical merits of each device, but the broader question of what role infantry rifles should play in modern scenarios. The decisive moment came not in a single test, but through a gradual realization among planners. The SKS worked. It was reliable, accurate and efficient. It could be produced at scale and maintained by personnel with minimal training. But the question of whether it should be the primary rifle was complicated by the parallel development of the AK-47. Kalashnikov's design offered automatic capability, which appealed to those who believed modern scenarios required suppressive fire. Yet the SKS had already been refined to a high degree of reliability, and its production could begin immediately. The decision was made to adopt both, but with different roles. The SKS would serve as the standard rifle, issued to regular personnel who needed a dependable, easy-to-use tool for general use. The AK-47 would undergo further refinement and eventually replace the SKS in frontline roles where rapid fire was deemed necessary. This compromise reflected the uncertainty of the moment, a recognition that doctrine was still evolving and that no single tool could address every tactical scenario. For Simonov, the adoption of the SKS in 1949 was a validation of his design philosophy. He had created a device that worked within constraints, that did not ask for more than it needed, and that solved a real problem. The rifle's semi-automatic mechanism and fixed magazine were not limitations, but intentional features designed to balance capability, control, and logistics. The short-stroke gas piston system was efficient and reliable. The tilting bolt was simple and robust. Every component had been tested, revised and refined until it functioned consistently under harsh conditions. The SKS entered production and began to be issued to various units. Personnel who had trained on older bolt-action rifles found the transition straightforward. The rifle's weight and balance were familiar, but the self-loading mechanism eliminated the need to manually cycle the system between shots. This increased the rate of fire without requiring new tactics. The fixed magazine, while slower to reload than detachable versions, proved adequate for most situations. The rifle was effective at common engagement ranges, and its reliability in cold, mud and dust made it well suited to the environments where it was deployed. Yet even as the SKS was being distributed, the AK-47 was being prepared for broader adoption. By the mid-1950s, the Kalashnikov rifle had proven its own merits, and the transition toward it as the primary infantry tool began. The SKS remained in service, but increasingly in secondary roles, issued to support units, reserve forces, and ceremonial guards. Its time as the frontline rifle was brief, but its influence extended beyond its years of primary service. The equipment had proven that intermediate cartridges and self-loading mechanisms could work together effectively. It had demonstrated that simplicity and reliability were not obstacles to performance, but foundations for it. And it had shown that engineering decisions made under material and industrial constraints could produce systems that functioned well in the real world, even if they were eventually superseded by designs with different priorities. The SKS did not disappear when the AK-47 took its place. It continued to be manufactured and exported to Allied nations throughout the 1950s and beyond. China produced millions of SKS rifles under the designation Type 56, issuing them for decades. Yugoslavia, Romania and other regions also manufactured variants, each adapted slightly to local production capabilities. The rifle spread across continents not as a symbol of innovation, but as a functional tool that worked. Its legacy is not found in revolutionary breakthroughs, but in the validation of principles that shaped later designs. The SKS proved that intermediate cartridges allowed personnel to carry more supplies, maintain better control, and engage effectively at realistic distances. It demonstrated that self-loading mechanisms could be simple enough for mass production and robust enough for harsh environments. It showed that restraint in design, choosing semi-automatic fire over full auto, a fixed magazine over detachable, could produce a device that met needs without overreaching. Sergei Simonov continued to work on designs after the SKS, though none achieved the same widespread adoption. He remained an engineer who worked methodically, who listened to the constraints of materials and manufacturing, and who built systems that functioned under pressure. The SKS was his most visible success, but it was also representative of his broader approach: clarity over complexity, reliability over theoretical performance, practicality over ambition. In retrospect, the SKS occupies a unique position in history. It was a bridge between the bolt-action rifles of the early 20th century and the automatic rifles that came to define modern infantry engagement. It was never the most advanced tool of its time, nor the most influential in shaping doctrine, but it was engineered with precision, built to solve a specific problem, and it worked. The quiet logic of its gas-operated system, the restraint in its design, and the context of its creation all point to the same conclusion. Sometimes the most important innovations are not the ones that change everything, but the ones that prove what is possible. The SKS was designed at the edge of one era and the beginning of another. It emerged from a moment when engineers were being asked to rebuild capability with limited resources and uncertain doctrine. Simonov's answer was a tool that did not promise more than it could deliver. It worked because it understood its role. It fired one shot per trigger pull because that was enough. It used a fixed magazine because that was sufficient. It locked and unlocked predictably, cycled reliably, and could be maintained in the field. These were not compromises. They were choices. Looking back now, the SKS reminds us that engineering is often about working within limits, about finding solutions that are good enough to matter. The device served its purpose, influenced later thinking, and then stepped aside for designs with different priorities. But it left a mark, not dramatic, not loud, but real, a mark that says, this worked, this solved a problem, this made sense at the time. And in engineering, that is often the highest achievement. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.